So let's pretend we have this reaction. We're told it's Sn2, and we know that Sn2 reactions proceed by inversion. And so we can predict the product relatively easily. We just substitute the chlorine for the Cn. Cn makes a very good nucleophile, and we take the wedge and we turn it into a dash, and so we've inverted the stereochemistry. And we can confirm that by assigning configuration. 1, 2, 3 here gives us R, and the cyanide is 1, 2, 3. Also gives us clockwise rotation, but again, the hydrogen is towards us. It's supposed to be backwards, so it's supposed to be towards the back of the page. So this is S. So we have inverted the stereochemistry. And what if we wanted to show the transition state? And we know that the transition state involves bond breaking. So we're going to show the chlorine bond sort of leaving. We're going to show the Cn bond becoming, creating a new bond as it acts as the nucleophile. And then we have the three substituents surrounding our central carbon here. So we're going to pretend this dot is the central carbon. This carbon here is the green dot on my transition state. And if we didn't have a stereocenter, it would be very easy to show this transition state. Just put the three substituents anywhere you want, and then draw the brackets around this with the double dagger that shows transition state. In this case, though, it's important to observe that we are inverting stereochemistry. So it matters where we put the three substituents around our central carbon, our chiral carbon that's becoming inverted. So I think an easy way to do this is to observe that I have a hydrogen here. That is one of the substituents, and then a methyl group, of course, and then the ethyl group. So I have substituents that are in priority 2, 3, and 4 in this case. And so it's going to be easiest for me to essentially, what I want to pretend is that this is one piece, and it exists in the R configuration. And I can do that if I put the 4 in the back, and I know that the chlorine is number 1. And so what do I need to count for R? I need to go clockwise. So number 2 needs to be right here on this wedge, and I'm going to just label that propyl quickly for now. And then number 3 needs to be on that bond. And so here it looks completely different than what I had before, but it is the same molecule. And if we imagine this dashed bond as being our original wedge, I still have the R configuration. I can count 1, 2, 3, and I get my clockwise rotation. And thus, this shows the chlorine in the right spot for essentially leaving, and then the Cn is coming in. So this is how I would draw my transition state. Now I'm going to erase all this extra stuff that I just put on here and make it a little more clear for you and show you the proper way of drawing it. But this is how you want to think about it. We want to make sure that the three substituents that are remaining around the carbon are arranged in the proper arrangement to show the inversion. Because if you just put them on randomly, you may show the other enantiomer. You may accidentally show me the S turning into R, which is the opposite direction that we're going in. So that's not going to happen here. So I need to extend this out so that it's 3 carbons. There's my methyl. And then, of course, I need a delta minus on the nucleophile. I need a delta minus on the electrophile. I need to erase this little parenthesis here and this, so it's not C with an exclamation point, it's just Cl. And there's my transition state properly drawn. So here I show proper stereochemistry. So that's very important if we have indeed a stereocenter that we start with and we create the inversion of that stereocenter for the product. If we didn't start with a stereocenter, like we could certainly show you, we could certainly do this as our Sn2 demonstration. We are not inverting anything because there's no stereochemistry right here. This is not a stereocenter, so it doesn't matter what I put on my transition state. I could just draw this. And there's my transition state. Doesn't matter where I put the methyls or the H because They are not describing any stereochemistry. So this is a much easier transition state to draw. But this one, I think, is very important for you to understand why we need to have these groups in a particular location. Now, if yours is drawn with the H up on top, the methyl coming forward, and the propyl going back, that's the same as what I have here. That's just a rotation around this imaginary dotted line. That's not changing the stereochemistry, that's just changing the relative orientation of my central carbon. So that's fine. I'm just showing you here an easy way to put everything onto the central carbon so that you retain that stereochemical information in your transition state.